Welcome back. Today our goal is going to be to get all the sizing of the aircraft done. So that's going to include the sizing of the wings, we're going to get a good estimate for the weight of the aircraft, we're going to get the location of the tail, all that sort of stuff. So the first thing we're going to want to find is our wing cube loading. And this is calculated based off of the wing area and the mass of the aircraft. So there's really two ways of going about this. If you already know what size you want the aircraft to be, then you can find the weight based on that in the wing cube loading. Or if you already know what the weight of the aircraft is going to be, say you have like a particular set of electronics you want to use, and you know what wing cube loading you want, then you can find the wing area that you need. So in my case, I know I'm probably going to end up around 1,300 grams, or 45 ounces, and that's just because I'm using the same electronics and the airframe is going to be about the same size as the other airplanes I've already built. So now the question is, what do I want the wing cube loading to be? Well, if we go over to this handy dandy online calculator, which I'll have in the description, we could put in 45 ounces, and then we could put it in a wing area, say, I think probably around 350 square inches is going to be right for that. So that gives us a cube loading of 11.9. It's not the actual wing loading, it's the wing cube loading. It's a slightly different formula, and basically it's more scale invariant. So a plane that's really small with the wing cube loading will have similar flying characteristics to a bigger plane with that same wing cube loading. Whereas if you look at the wing loading of actual full-scale airplanes, they're a lot different than the model scale, whereas the wing cube loading is sort of similar. So they give some typical cube loading values for models, which are, this is a fairly good suggestion here. The Efflux Mk, which I had, was around 13, so it's definitely on the top end. It's a high-performance jet. And then the Efflux Mk was around 17, so that was quite large. And I like the flight characteristics of the Mk better. It was definitely a lot easier to fly, less on edge. So I'm probably going to be shooting a bit towards that 13 or maybe less. So I think probably around, probably maybe 330 would get me to wing cube loading of 13. But I think I'm going to go just a bit lower because we're going to be doing high alpha. I want to have a bit of extra margin. So we're aiming for a wing cube loading of around 12. And that means we have 350 inches squared of wing area. So now the next thing we can do is actually start to model that. So this is Google Sketchup. This is the program I use to design all my aircraft. This is Sketchup 2017. They don't actually distribute this version of it anymore. You can find downloads of it. I'm not sure if they're quite legit, but this is what I use along with some plugins, which I'll have down in the description. The two plugins are an Unwrapping plugin. So for example, if I make a box here, and then I select the faces of the box, and then unwrap that. This is what I use to basically unwrap the geometry of my plane so that I can print it out and then cut it onto a sheet of foam board. And then I also use an SVG exporting plugin so that I can export this into an SVG, which I used to use in the past for laser cutting, but now I just use so that I can get it in a more convenient format to print because SketchUp doesn't print stuff that well. I'm not going to go over how to use SketchUp in this series. Really, there's a lot of tutorials out there on how to use it, and really you don't have to use SketchUp. Any CAD software that has the ability to unwrap faces like that and then export them in some way that can be printed will work for this. So anyways, let's get started on our wing here. So that's fairly low aspect ratio, greater than 45-degree sweep at least. Yeah, so that's 2.45 foot squared, which is, yeah, so that's the 352 square inches we need. And I'm looking at this and I'm thinking it could probably be a bit lower sweep. And you also have to consider that the fuselage is going to take up some of this area here. So this area won't get included in the wing area. So we probably want to make this a little bit oversized. And this is just basically by eye. The wing sweep I'm choosing here is just what looks good, really. And then I can move this point back until it gives me about the area I want. Figure that's probably going to be around the width. Yeah, so that's right on pretty much. Yeah, 350 inches squared. All right, that's perfect. So this is going to be our wing planform. And now we move on to sizing the canard. The first thing we want to figure out is how big the canard is going to have to be there's something called the horizontal tail volume ratio, or horizontal tail volume coefficient. And there's basically a formula for calculating it, and there's a bunch of numbers here for typical values of the horizontal, and there's also one for the vertical stabilizer. So basically, you want to figure out what type your plane is and then pick your horizontal tail coefficient so that it's around what you need it to be. So generally, the higher the horizontal tail coefficient, the more adverse pitching load or CG shift you're going to have to deal with. So if your plane has big flaps, or if it's carrying a payload, or it needs to carry payloads that might be before or after the CG, or it has to deal with CG shift in flight, generally you want this horizontal tail volume coefficient to be bigger. I also need to consider that the tail, or the canard, isn't doing much stabilizing because it is basically more or less just a delta wing. So we can probably get away with way lower than this, maybe around 0.1 or 0.2. In fact, it probably doesn't matter much at all, because even if you didn't have a canard, you could still get it to balance just as a delta wing. And we do have elevons that we'll be able to use for that. We're going to basically just draw ourselves about where we think the canard is going to be. So now, based on our horizontal tail volume coefficient, we can use these estimates and then put them into the center of gravity calculator. And then we'll see if that volume ratio turns out to be what we need it to be. And if not, we'll tweak it around until it does. And typically around 50% static margin will give you a good CG estimate. So this is a bit small. I think I could get this probably around 0.1, and that'll give us just a bit more control there. It'll move the CG further forwards. Let's move those up and then probably make them a little bit bigger. So there we go. There's our 0.1 for the canard volume ratio. And that's what our planform is looking like. And so if we look down here to see where the CG is, we go from the canard root leading edge to the CG is 15.61 inches. So somewhere around here is going to be the CG for this. And that'll probably be forward of the actual CG, because that's a 15% static margin. Now we can work on our vertical tail. So the main factor with this one is, do you have any big torques in yaw on the airplane? If your airplane is a single engine, propeller driven, you're still going to have to deal with P factor and all of the left turning tendencies that come with that. So you're going to want a larger vertical tail than, say, a sailplane, which doesn't have any of that torque problem. If you have two engines, generally you want to just about double the size of your vertical tail to deal with an engine out scenario. This is a ducted fan aircraft, and the amount of left turning tendencies that these have is pretty much non-existent. You do get a bit of torque roll, but it's not much at all. It's not to the level that you can feel it, at least. I also want to consider that we're going to be in high alpha, and when you're in high alpha, your elevons won't do much in terms of rolling the aircraft. Mostly it'll be done by yaw. So we will have thrust vectoring to help it out, but I still would like to oversize the rudder just to help out with controlling the aircraft at high angles of attack. So we'll probably shoot for around 0.03, 0.04. And so what that means is we can go to this formula here. So that vertical tail volume ratio is going to be our vertical tail area times its distance to the CG of the aerodynamic center of the tail, which is around the quarter chord of that tail, divided by the wing area times the wingspan. So we know approximately 3 of these. We know more or less how far the tail is going to be. It's going to be at the very back of the wing. We know the wing area and we know the span, so then we can use that and our desired vertical tail volume ratio to calculate how big it's going to have to be. So that gives a vertical tail area of approximately 17.6 inches squared. I mean, this is probably going to be around the size that it'll end up being. That's actually bigger. And I'm thinking about it, this looks fairly small. I think we're going to go probably a lot larger on the vertical tail here. So something around that seems reasonable in terms of sizing. So then this thing, the quarter chord of this, is probably going to be somewhere around here. And so that's going to be about 16 inches. It's got an area of 26.6 inches, so we can do the math. So that gives us a vertical tail volume ratio of around 0.05. And I think that's pretty good for what we need it to do. So now we have a pretty good idea of where the aerodynamic surfaces of everything are. And the next thing we need to do is to figure out where we need to place all the electronics components in here to get the CG in the correct location. So I actually have CAD models of the Efflux Mk II here, and I have CAD models of all the electronics inside it. So I'll just extract those right now. The battery, the flight controller, the ESC, the ducted fan, the main gear, and the nose gear. Also, a general rule of thumb is that foam board is 115 grams per sheet. A sheet is 20 by 30 inches, and you got to keep in mind that you're going to be folding double layers for the wing, plus glue, plus internal spars. So typically, a good estimate of the weight of the wings is to take its area and then multiply that by 3 times the weight of whatever this area of foam is. And that'll get you pretty close to what the weight of it will be. And then for these will be just single sheets of foam. And then you'll take the area, multiply it by maybe 1.25 for, say, for leading edge reinforcement, the servo arms and the hot glue and the hinge, that sort of stuff. So now we can start a table basically with every component of the aircraft and its estimated mass. So these here are in grams, and then I'll be going into CAD and then changing the position of those with respect to the CG in inches. And then I multiply those two together to basically get the moment of that bit of mass acting at that bit of distance. And then down at the very bottom, we sum up everything, and we get an estimate of the mass. And then we divide that by the sum of the weighted distances to get the CG location. And this distance is measured to whatever reference you want it to be. So basically what I'm going to do is I'm going to place all these components around in CAD and estimate their distances, and then tweak those around so that we get the CG in the location we need. It's important here to note also that you're going to have different signs for things in front of or behind the CG. So for example, this nose wheel here is going to be positive for being in front of the CG, and then the main gear will be negative for being behind it in terms of the distance. And it doesn't matter whether you use positive or negative, just as long as you use it consistently, so that things behind are always one sign and things ahead of the CG are always the other sign. For EDFs, a good rule of thumb is that you want the thrust tube to be about 4 times as long as the diameter of the EDF. So the diameter is about 3 inches, so I'm going about 12 inches from the end here. So that's the CG with everything laid out as I have now. And so we can see that it's fairly far forward. And so what I can start doing is playing around with the locations of stuff to try and move that CG backwards. Another thing we can do also is alter the airplane aerodynamically so that the CG could be further forwards and meet the CG that we currently have. So that would be like enlarging the canards or making the main wing smaller, stuff like that. Alright, and so that's a solution that gets us pretty much to 0 on that CG location. And so that's probably a pretty forward CG, and so if we need to move it aft, we should have plenty of adjustment range. So I'm able to move the battery maybe around 3 inches aft, which will be able to move the CG about 1 inch aft. So that's pretty good. And this is 5% static margin that's probably super unstable. So in between these is 10%, and then this is 1 inch, so that's probably around 12%, which is pretty good. Anyways, that's it for this episode. We've completed the basic sizing of our aircraft, and we know approximately where all the components are going to be. So the next step in the next episode is going to be just to start CADing everything up and getting an idea more precisely of where everything's going to go. And until then, I'll see you guys.